In this video, we solve problem 3.1.9. Now, this is from a differential equations textbook, but it is not the Nagel Fundamentals of Differential Equations textbook that we are using in our course during the spring 2021 semester. I pulled it from a different textbook in MyLab Math, which is a Pearson text. When you use MyLab Math to create quizzes, you are allowed to use other textbooks, but unfortunately, it's not easy for me to look up which textbook this came from. So I apologize for that. But this is problem 3.1.9 and some Pearson text, which is not the Nagel differential equations text. Here's the problem statement. This says a homogeneous linear second order differential equation, two functions y1 and y2, and a pair of initial conditions are given. First, verify that y1 and y2 are solutions of the differential equation. Then find a particular solution of the form y equals c1 y1 plus c2 y2 that satisfies the given initial conditions. Primes denote derivatives with respect to x. So we've got our differential equation, we've got a y1 and a y2, and we've got these two initial conditions. Okay, first it says, let's verify that y1 and y2 are solutions of the differential equation. And that's pretty straightforward. In order to verify that a function is a solution of an equation, you just substitute it in. But since this is a differential equation, we've got to take the derivative. Since it's a second order differential equation, we have to take the derivative twice. So we'll start with y1 equals e to the negative x, and then we will compute y1 prime and y1 double prime. Derivative of e to the negative x is e to that power times the derivative of the inside by the chain rule. The derivative of negative e to the negative x, oops, that's a first derivative, and that's the second derivative of y1. The second derivative comes from bringing the negative down and then taking the derivative of e to the negative x again. Derivative of e to some power is e to that power times the derivative of the inside, which is another negative 1. Negative 1 times negative 1 is, of course, positive 1. So these are our derivatives. Now, if y1 is a solution of the differential equation, I should be able to substitute into the left-hand side and get the right-hand side. So we'll substitute in the left-hand side first. y1 double prime plus 2 times y1 prime plus y1 is equal to y1 double prime, that's e to the negative x. Then we're adding 2 times y1 prime, which was negative e to the negative x. And then we're adding y1, which was e to the negative x. And when we do that, let's distribute that negative, we get this. We've got 2 of those, and you're subtracting 2 of those from that. They're all gone. And that means we get a 0, which is equal to the right-hand side. So we substitute into the left-hand side and show that the left-hand side equals the right-hand side. If you can do that, then you have verified that that function is a solution to the differential equation. Now we're going to do the same thing for y2. So now I'm going to just use the same steps over here, but I'm going to do y2 prime and y2 double prime, and then we'll substitute into the left-hand side and show that the left-hand side equals the right-hand side. But this time when we take the derivative, we've got to use the product rule. So I've got a function of x times a function of x. The derivative of a product is derivative of the first. Derivative of x is 1 times the second, undifferentiated, plus the derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside, which is negative 1, times the first. And if you want, you can factor out the exponential. So we'll have e to the negative x times 1 gives us our first term, and e to the negative x times negative x gives us our second term. This is our first factor, and that's our second factor. So when we take the derivative again, we have to use the product rule again. We'll have this time derivative of the first. Derivative of e to some power is e to that power times the derivative of the inside. times the second undifferentiated plus the derivative of the second, which is just 0 plus -1 or -1 times the first. And if you distribute, you get this. And if you want, you could factor out the exponential, but I think it's probably better to leave this expanded. And I think I'm going to use the expanded form of y2 or y sub 2 prime when I substitute into the differential equation as well. So now we're going to take these guys and we're going to substitute into the differential equation, much like we did with y1. So y2 double prime plus 2 times y2 prime plus y2 is equal to first y2 double prime, which is right there. So I've got x e to the negative x minus 2 e to the negative x plus 2 times y2 prime, which in expanded form is e to the negative x minus x times e to the negative x plus y2, which was x e to the negative x. We can distribute that 2. It was distributed there and there. And see if anything cancels out. Well, I've got 2 of these. Those are gone. And I've got an x e to the negative x and another x e to the negative x. So that means I have 2 of those, and then I'm subtracting 2 of those. So those are gone. So we get 0. So the left-hand side does equal the right-hand side, which means that y sub 2, which is x e to the negative x, is a solution of the differential equation. Okay, so they asked us to verify, and we just did. Now the next part says, find a particular solution of this form, y equals c1y1 plus c2y2 that satisfies the given initial conditions. Now, when I saw that, I'm thinking my students may be confused because they wouldn't think of that as a particular solution. They think of that as a general solution. And you're right, when we use the c1 and c2 there, and they're just arbitrary constants for right now, that is the general solution. But they're saying, we want you to find a particular solution that has this form for particular constants, C1 and C2. So we actually have to find C1 and C2 for the initial conditions and then substitute into that form. So I know that this looks like a general solution. They're just saying they want a solution that's in the form of a general solution, but with the constants substituted, the appropriate constants that will allow the solution to satisfy the initial conditions. Okay, so that's the plan. So let's write down our general solution. So we have y equals c1 times y1, which is e to the negative x, plus c2 times y2. And here are our initial conditions. We know that y of 0 is supposed to be 9, and y prime of 0 is equal to -6. Now, those 2 conditions will get us 2 equations with 2 unknowns. Sometimes we're really lucky, and one of them immediately simplifies to 1 equation and 1 unknown. And so we'll just get 1 constant, and then it's easy enough to find the other constant using the other condition. And sometimes we end up with 1 equation, or 1 equation with 2 unknowns, and a second equation with 2 unknowns. So we end up with 2 equations and 2 unknowns, and we have to solve by using our methods for solving systems of equations. It really just depends on what y is. So this is my general solution. I'm trying to find C1 and C2. In order to find C1 and C2, we can use the first initial condition. This is telling us, remember, that when x equals 0, our y value is 9. So we can substitute in x equals 0, we can substitute in y equals 9, and then there will be no x's and y's. Those will be gone, and we'll just have an equation involving C1 and C2. And then we can simplify that as much as possible. So I will substitute x equals 0 here. So y of 0 equals this. And of course, 0 times anything is 0. E to the 0 is 1. And of course, the opposite of 0 is just 0. So we end up with C1. So no matter what C1 and C2 are, y of 0 will equal C1. And now we're saying we want y to equal 9 when x equals 0. So we're going to set this result equal to 9, which clearly tells us that C1 equals 9. That's nice. We got C1. Now to find C2, we're going to have to use the second initial condition. And to use the second initial condition, we need to substitute into the derivative of y. We need to replace x with 0 and the derivative with -6. That means we need to compute the derivative. So we have our y here. Y prime is this. Bring your constant down. The derivative of e to some power is e to that power times the derivative of the inside, which is -1. Bring your constant C2 down. Or actually, if you want, you could think of this as a product of a first function and a second function. We'll have derivative of the first, which is C2, times the second, plus the derivative of the second, which is e to the -x, times -1, derivative of the inside, times the first. Okay, so y prime turns out to be equal to -C1 e to the x plus C2, and let's factor out the e to the x is e to the -x as well. C2 times e to the -x times 1 to give us that term, and C2 times e to the -x times a -x to get us that term. Because I'm looking at these two guys and I'm saying they've got this C2 in common, they've got the e to the -2x in common. If I factor those out, what's left? This times 1 would give me this, and this times -x would give me that. Okay, so that's y prime. Now let's evaluate this at 0, because we know our second initial condition is that y prime of 0 is equal to -6. So that means that when x is 0, y prime is -6. So let's figure out what y prime would be in general in terms of C1 and C2, and then we'll set that result equal to -6. So y prime of 0 is going to be C1, or this. Well, I'll just write this down. I'm just using parentheses as a placeholder for x, and then replace all my x's with 0. E to the 0 is 1. 1 times 1 is 1. And so we get -C1 plus C2. That's what y prime of 0 would be, no matter what initial condition is given. Y prime of 0 for this particular y would be -C1 plus C2. Now we're going to set this equal to the known y prime value. We know that y prime is -6. So we have C2 minus C1 is -6. But remember, we already found C1. C1 turned out to be 9. Since we know that C1 is 9, we can substitute that in here and solve for C2. Add 9 to both sides, and you'll have C2 equals 3. So when C2 equals 3 and C1 equals 9, y equals C1y1 plus C2y2 is a solution of the differential equation. So this is a particular solution. When I substitute C1 equals 9 and C2 equals 3. Okay. And that is both parts of the answer to that problem. MyLab Math wanted you to enter it in a particular way. I think they asked you to type in the first and second derivative of y1 prime and y2 prime, or the first and second derivative of y1 and y2, excuse me. And that's fine. But for our quiz, like I'm looking for something like this. I just want you to answer this question, and I'll be grading your paper, not your MyLab Math work. So focus on justifying your solution and actually doing what they ask you to do. And then as long as you did that and you did it well, you did it correctly, then you will get full credit and get an A on this particular standard, which is about preliminary theory for higher order differential equations.